A modern central processing unit can execute billions of instructions per second, but that processing power is entirely dependent on the delivery of data. When a CPU exhausts its internal cache, it sends a request to system memory. If data does not arrive instantly, the entire processor stalls, waiting on a trickling input stream. This chart plots the memory wall. The aggressive upward curve is the exponential growth of CPU peak throughput. The flat line represents DRAM access latency. This physical gap represents thousands of wasted clock cycles, creating the dominant performance bottleneck. DRAM functions as a high-speed buffer, using complex architectural layers to hide delays in data retrieval. To understand exactly how a system dictates performance, we have to examine them. This schematic shows the 1T1C cell. It consists of one transistor and one capacitor. This is the atomic unit of dynamic random access memory, or DRAM. The mechanics are binary. An electrical charge filling the capacitor represents a digital 1, and an empty state represents a 0. To read the data, the word line triggers the transistor. This acts as a microscopic switch, allowing the charge to flow out of the capacitor and down the bit line to a sense amplifier. A single memory chip contains billions of these cells arranged in a massive grid. The total capacity of that chip is calculated by multiplying its addressable rows by its columns and then by the number of internal banks holding those grids. To increase capacity without changing the physical chip footprint, manufacturers shrunk the silicon fabrication process, fitting 24 gigabits worth of cells onto the same size die that previously held 16. This non-binary density is what allows for 24 and 48 gigabyte modules. Managing this dense grid requires the integrated memory controller, a dedicated logic block located directly on the CPU. The controller orchestrates every action, sending the precise voltages to pre-charge the bit lines and activate the word lines. The controller reads this data in 64-bit wide blocks known as a memory rank. A single rank module has one of these blocks. A dual rank module places two independent 64-bit blocks on the same printed circuit board. Dual rank architecture allows the memory controller to perform rank interleaving. Because DRAM capacitors constantly leak charge, they must be periodically refreshed. While one rank locks down to run its refresh cycle, the memory controller simultaneously queries the second rank for new data. The resulting architecture provides the memory controller with a matrix of parallel pathways, ensuring a continuous flow of data even while individual banks are cycling. When evaluating how fast those lanes operate, consumers look at frequency. Measured in higher advertised speed actually takes 25% longer to respond. For random access workloads like a real-time game engine, the CPU makes constant, unpredictable data requests. Achieving that 10 nanosecond absolute latency prevents the processor from stalling, ensuring a smooth stream of rendered frames. These performance targets are limited by the physical electrical characteristics of the DRAM chips themselves. No two chips are identical because of the inherent microscopic variations that occur during semiconductor fabrication. To identify these differences, technicians use electronic die sort to measure these variations, sorting every chip on the wafer into a performance tier. Chips that tolerate high voltages and aggressive clock speeds without leaking current are sorted into premium bins. Chips with higher leakage or slower switching times fall into standard bins. When you buy a high-performance memory kit, you are paying for the highest bin silicon. Advertised speeds are a direct physical reflection of that silicon's electromagnetic purity. Moving that data out of the pure silicon requires navigating the copper traces of the module's printed circuit board. At multi-gigahertz DDR frequencies, these copper traces stop acting like simple wires. They become complex transmission lines. Every pulse of data generates a wake of electromagnetic interference that can distort the surrounding signals. This CAD visualization reveals the layout of a memory PCB. Engineers use electronic design automation software to enforce strict physical constraints, resulting in this zigzag serpentine routing pattern. This technique is called trace length matching. Electrical signals on this board travel at a fraction of the speed of light. Because the physical pins on a memory module are at different distances from the memory chips, straight traces would result in data arriving at different times. Serpentine routing artificially lengthens the shorter paths, so all signals arrive at the memory controller at the exact same picosecond. If these traces are routed just a few millimeters too close to each other, the electromagnetic wake from one channel bleeds into the adjacent lane. This crosstalk corrupts the data before it ever reaches the processor. Pushing high voltages through these dense traces generates concentrated heat. To prevent the copper from warping, designers drill microscopic vias, copper-plated holes that pull heat away from the silicon and sink it deep into the internal layers of the board. The modern RAM stick is a highly tuned electromagnetic containment vessel. The geometry of the copper dictates the survival of the data. When you install the highly stable, clean voltage supply required to maintain signal integrity at extreme frequencies, DDR5 memory modules function as autonomous power subsystems, managing their own voltage regulation independent of the motherboard they are seated in. Squeezing billions of 1T1C cells into denser silicon introduces severe physical vulnerabilities. The capacitors are so microscopically small that stray cosmic radiation or dense localized electrical traffic can destabilize neighbors and flip a 0 to a 1. This is known as the Rowhammer effect. When a memory controller rapidly and repeatedly toggles a single word line, the resulting electromagnetic leakage physically discharges adjacent capacitors, altering data without any formal write command. To prevent this corruption, DDR5 includes error-correcting code directly on the silicon die to catch internal manufacturing faults. However, this, or PIM, places the logic compute cores directly inside the RAM itself. The memory wall cannot be defeated by simply forcing higher clock speeds over copper wire. To eliminate the latency bottleneck, the next generation of computing relies on destroying the physical distance between data storage and processing.